Alright, welcome back, guys. So we finished up 8.3, and the last thing that we were doing in 8.3 we're actually going to start with in 8.4, or at least the results from that. And that is, if you know the zeros of a polynomial, you know its factors, and vice versa. Okay, so if you remember, that theorem was called the factor theorem. And it said if we had, some polynomial, I'll just make one up here. Let's say it's in factored form. Okay, so it looks like this, and we can call it f of x. Okay. So this would be a quadratic polynomial, but it's in factored form. Well, when it's in factored form, it's easy to find those zeros. You just set the factors equal to 0. Okay. And so if you set each of these factors equal to 0, then the zeros are going to be basically the opposites of those constants in those binomial factors. Okay? And so the factor theorem just says that we can work backwards. If we know that the zeros are 2 and 1, then the factors had to have been x minus 2 and x minus 1. Okay? And so that's what we're going to start out with. We're going to start to reconstruct a polynomial when we're given its zeros. Okay? So up until now, we've been given a polynomial and asked to find zeros. Now we're going to be given the zeros and asked to find the polynomial, or at least to express it in factored form. Okay? Let's look at this theorem, right? The fundamental theorem of algebra here real quick. It just says that every polynomial with degree greater than or equal to 1, so this means a linear function, a quadratic, a cubic, a fourth degree, etc., all the way up forever, will have at least one zero that's a complex number. Okay? So every single polynomial is going to have at least one complex zero. Now remember the difference between a real number. A real number is just a number on the x-axis. Okay, and they can be rational or irrational numbers. But a complex number is not only the real numbers, but it also includes those imaginary numbers or some combination thereof. Okay, so when it says that every polynomial will have at least one zero that's a complex number, think about, we saw some examples with those quadratic functions. Sometimes the zeros weren't real, they were imaginary, or a combination of a real and imaginary. Well, that's complex. Okay. And then furthermore, every polynomial function of degree n can be factored into n linear factors. Okay, and this is not necessarily unique. That just means that some of the zeros might have multiplicities greater than 1. Okay, so this piece of the theorem right here is just what we were talking about. If we know the zeros, we can know the factors, and so every polynomial can be expressed as a product of its factors. All right. Okay, so what we're going to be doing now is we're going to be given some zeros of a polynomial. They're going to tell us the degree of the polynomial, and they're going to ask us to find the polynomial. Okay, so we're going to be working backwards. So let's look at example 1. It says find the polynomial, or the polynomial of degree 3 with real coefficients and whose zeros are these numbers, -2, 1, and 5. Okay. So I'm going to state that the zeros are -2, 1, and 5. Okay. Well, there's 3 distinct zeros here, and this is a third degree polynomial that we'll be finding. Okay. So now I'm going to use the results from that factor theorem it basically tells me that if I know my zeros, then my factors are going to be, well, they're going to be linear, and the constants of those factors will be basically the opposites of these zeros. So if negative 2 is a 0, then x plus 2 will be a factor. And if positive 1 is a 0, then x minus 1 will be a factor. And finally, if 5 is a 0, then x minus 5 will be a factor. Okay? Now, once we know the factors, how do we find the polynomial? Well, we just multiply the factors together. Okay, so the polynomial that we're searching for is a product of its factors. Oops. Plus, yeah, I had that. Now that should be minus. Yeah, there we go. And so what we'll do to find this polynomial, or at least to express it in standard form, is we need to actually multiply these factors together. Okay. And so I'm going to kind of come up here, and I'm going to multiply my first two binomial factors together first. Remember, we do these two at a time. So x times x is x squared. X times negative 1 will be negative 1x. And then we'll distribute the 2 here. 2 times x will be 2x. 2 times negative 1 is negative 2. You should always be able to combine these two middle terms. That'll give me just 1x, so I'll have x squared plus 1x minus 2. And we'll keep that in parentheses, and now I need to multiply this trinomial here by this last binomial factor, x minus 5. Okay? And so you're going to do this. We've seen this before, guys. You're just going to say x squared times x will be x cubed. X squared times negative 5 will be negative 5x squared. Then you're going to distribute this x right here. X times x will be x squared. X times negative 5 will be negative 5x. And then finally distribute your negative 2. Negative 2 times x is negative 2x. And negative 2 times negative 5 is positive 10. And so now if I combine my like terms, negative 5x squared plus 1x squared will be negative 4x squared. I'll keep my x cubed. Negative 5x minus 2x will be negative 7x. And I'll have that plus 10. And this right here, guys, this is my polynomial. This is a third degree polynomial whose zeros will be negative 2, 1, and 5. Okay? To prove it to you, we're going to graph it. So x cubed minus 4x squared minus 7x plus 10. Okay, and now let's look at this. I don't know why this is messing up on the bottom. Look and see where it crosses the x-axis at negative 2, positive 1, and at 5. Okay, just like we said it would. And it crosses because it has 3 zeros, and since it's a third degree polynomial, that means each of these zeros must have multiplicities of 1. They occur once, right? And 1 is an odd number. So that's why it's crossing at all those values. All right. Let's go to example 2. This may be a 3-part video, guys, because there's quite a bit of material in this section. All right, example 2. we're doing the same thing here. Write a polynomial in standard form with real coefficients, and then it lists the zeros again. Okay, so there's 3 zeros. You'll notice that 2 of them are actually purely imaginary. I'll do this in the same way. Go ahead and list my zeros. -2, 3i, and -3i. And then I'm going to list my factors. Okay? Because from the factors, from the zeros, we can obtain the factors. So if -2 is a 0, x plus 2 will be a factor. And then if 3i is a 0, x minus 3i will be a factor. And if -3i is a 0, then x plus 3i is a factor. Okay? And so now, to construct our polynomial, or to express it in standard form, we just need to multiply all these together again. But I'm going to give you a tip here. When you do if you have any with imaginary zeros, go ahead and multiply those corresponding factors first. And I'll show you why this is a better way. Because technically the order in which you multiply those factors doesn't matter. But multiplying these two together first will make this a little bit nicer, or cleaner. Alright, so x times x is x squared. X times 3i will just be 3ix. And then on the inside here, -3i times x will be -3ix. And then finally, -3i times +3i is -9i squared, because you're multiplying an I times an I. Okay. Now, what you're going to notice is those terms in the middle, they're opposites. It doesn't matter if their coefficients are imaginary. They will cancel. And that's one of the reasons I suggest that you multiply these two factors together first. These are known as conjugates because they're basically the same. It's just that this constant right here, the constants have opposite signs. And so whenever that's the case, when you multiply these two middle terms are always going to be the same, but with opposite signs. Okay, so I have an x squared left. Now, to evaluate this part here, we need to think back about the definition of I. It's the square root of -1. Well, I don't just have I have I squared right here. So what happens when you square I, you get the square root of -1 squared. Well, what happens when you square a square root? Well, those are inverse operators, okay? Or in other words, they undo each other. So when you square a square root, you just end up with whatever's underneath it. So -1. So I squared, this goes back to the definition of what I is. I squared is -1. Okay, so what you're going to do here, guys, is you're going to substitute I squared with -1. And so you end up with -9 times -1, and this will turn into a +9. So you'll end up with x squared plus 9. Okay, go ahead and keep that in parentheses, because now you're going to multiply it by this last binomial factor, which is x plus 2. So see, instead of getting a trinomial here like we did in the previous example, we have just a binomial. So that makes this a little bit easier. Alright, so we're going to FOIL these. X squared times x is x cubed. x squared times 2 will be 2x squared. And then we'll distribute the 9. 9 times x is 9x. And 9 times 2 is 18. And we are done, guys. This is our polynomial with these zeros in standard form. Now if we were to graph this one, we'll only see it cross the x-axis at -2, because that's the only real zero. These other two are imaginary. Okay. All right. And you could graph this one if you want to check. I'll go ahead and do it for us real quick. Plus 18, I think. Okay. Let me just double check. Yeah, that's it. Alright, so if you're looking at this, you may think, whoa, that's weird. It's cubic, but it doesn't look all that cubic. But it is, guys. It's, you know, it's only crossing right here at -2. That's the only place it's going to cross the x-axis. And it kind of goes across right here, so it still has that kind of that cubic behavior. But it never actually decreases anywhere. This is just a strictly increasing function. I don't know why this is misbehaving again. Okay. Well, anyway. Alright, let's do... Well, let's definitely do example 3. This is the same question. It says we want to find a polynomial of degree 4, and then it tells us what the zeros are. But it actually tells us what the multiplicities of these zeros are. So in the previous example, we just assumed that the multiplicities were all 1. Okay. But in this case, we're going to have -3 as a 0, but it has multiplicity of 3. Okay. So it's like it occurs 3 times. So when I go to list my zeros over here, I will write it 3 times. And then my other 0 is 0. Well, it has a multiplicity of 1. Okay. So it just occurs once. Now I can express my factors. Well, I'll have 3x plus 3's as factors, right? Now, if 0 is a 0, then x minus 0 should be a factor. But we typically don't express it as x minus 0. Okay? Because what does x minus 0 simplify to? Well, x minus 0 is just x. Okay? So typically, now the book might show you x minus 0, but it's just going to simplify to x. So anytime you have 0 as one of your zeros, your corresponding factor is just going to be x. Alright, well these are all my factors that I need to multiply together to get my polynomial for this one. Okay. Alright, so start out with the 2x plus 3's. Guys, let me run through this kind of quick. X squared plus, you can get a 3x plus 3x plus 9. Those two in the middle will become 6x. Okay, but then we need to multiply that by our other binomial factor, our other x plus 3. So you'll do the same thing again. And you're going to get x cubed plus 3x squared, and then distribute your 6x squared, and then times 3 will be 18x, and then you're going to distribute your 9, we get 9x and then plus 27. Okay. And then we'll combine our like terms. We'll have x cubed plus, that'll become 9x squared. Our two x terms will become 27x. We've got that plus 27 at the end. Now technically we're still not finished because we've got this last factor of x. Well, this isn't going to be bad because if we multiply all these terms by x, their powers are just going to go up by 1. Okay. So we're going to get for our function x to the 4th plus 9x to the 3rd plus 27x to the 2nd plus 27x. So we end up not having a constant, or you could say our constant is 0. Okay, and that's it. This is a 4th degree polynomial here, if you notice. Now I want to graph this one for you as well. Oops, x to the 4th there. Okay, that's it. Now let's come back over here. Our zeros were -3 with a multiplicity of 3, so it's odd. 0 with a multiplicity of 1, which is odd. So with those two zeros, we should see the function crossing the x-axis. And that's what we see. It crosses right here at -3, and then it crosses over here at 0. Okay? And this is a 4th degree polynomial. All right. Okay. Well, guys, I think I'm going to stop the first video. This is a good stopping place. And then we'll cover kind of the middle half in our second video. The next 3 examples, and then the last piece in our third video. Okay. Alright, so I'll see you in a bit.